Welcome back, everybody. This is our video solution to problem 4 from Quiz 9, Fall 2023, Math 307, Linear Algebra at Cal State Fullerton. All right, let's see what we got. We have a finite-dimensional inner product space V over a field F. Of course, F is going to be the reals or the complex numbers for us. And we have a linear functional phi from V to F. We want to state and prove the existence part of the Riesz representation theorem for V and phi. All right, so the Riesz representation theorem is going to tell us that we can write this linear functional as really just being the linear operator given by taking the, not linear operator, but linear function given by taking the inner product of an element with a very particular specific element, which we call the Riesz element. So let's write this down. So at least the existence part, right? So, of course, there's a uniqueness portion, but we'll just write the existence portion. So the Riesz representation theorem is going to tell us that there exists some particular element u in V such that for all V and V, if we apply phi to V, it's actually the same thing as taking the inner product of V with this particular element u, or I think in class we called it u sub phi. All right, so now we'd like to prove this. And the nice thing is, once we did the proof in class, we kind of knew this u phi is given very constructively. So we can just write that down. So the first thing we did is we said, well, let's take an orthonormal basis for V, right? We know that's always possible. We can use the Gram-Schmidt method. So we'll let E1 through En be an orthonormal basis for V. And so we're going to define u sub phi, this is our Riesz element, to equal, well, it's just going to be you apply phi to each of these basis elements. That gives you some element in F. Take the complex conjugate, and then multiply by that same basis element. All right, and I'm using Einstein notation here to keep this simpler, right? So this means we're summing over the i's. We've got an I down below and an I up above. All right, and so our claim is, of course, that if I apply phi to any V and V, it's the same thing as taking the inner product of V with this u phi. All right, well, how can we see that? Well, we're going to verify it by, well, first we can write V. So we have V itself. All right, maybe we'll take some V and V, right? Okay, let V and V and V. When we have V is equal to, well, of course, we can write it in terms of the orthonormal basis. And we actually know what the coefficients are. They're just the inner product of V with each of these coefficients. All right, I'll write actually with a J this time. All right, so as not to maybe confuse it. Okay, so we know what V is, and so now we want to compute phi of V. So phi of V, well, this would just be phi of this sum, right? We have the inner product of V with EJ times EJ. Oops. Okay, but I can pull these coefficients outside of each of the phis. So I have V, EJ outside, and then I'll be doing phi of EJ on the inside. Now the phi of EJ, this is just some element of F, right? This is just, right, because phi is a linear functional, so this is just some element of F. So I can actually move it inside the inner product. I could put it either into the first or the second component. And in this case, I'm going to actually put it into the second component so that I keep all the EJs together. Now, when I put it into the second component, of course, I'm going to have to put a complex conjugate over it. So this will become V, then I have phi of EJ, complex conjugate, EJ. Okay, again, I still have one up and one down, so there's still a sum over F, or over J, rather. Oh, but other than this being a J instead of an I, we go back and look at our definition of the u phi. That's exactly it, right? Like we're summing over J, and we're taking phi of EJ bar times EJ. Well, okay, here it's over I, but it doesn't matter. So this is actually the same thing here as u sub phi. And therefore, if we apply phi to v, it's actually the same thing as taking the inner product of v with our proposed Riesz element u sub phi. Okay, there we go. We've found the Riesz element. We have verified the existence portion of the Riesz representation theorem. Okay, we will see you next time.